Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be solving a very nice question on gravitational fields. So the question reads, we have two planets, we have the radius of each planet, and we have the density of each planet. Now we have been told that the gravitational field strength at the surface of the first planet is 13.4 newtons per kilogram. Now we are asked to find the gravitational field strength at the surface of the second planet. So I'll try my best to explain detailedly so that you understand the concepts behind this. Alright, so first of all, what is gravitational field strength? Think about anyways, what is gravitational field strength? What's the symbol? It is G. Alright, so it's the same as acceleration due to gravity, but it's actually a vector because it has direction as well as it has magnitude. So that G that we know as acceleration due to gravity is also called the gravitational field strength. Alright, so the first assignment I'm giving you is what is the definition of the gravitational field strength at a point. Anyways, normally if a body is on a planet, if you are on the surface of a planet, for example, let me say we are on the surface of Earth, right? Now there is a force that exists between us and Earth because we have masses. We have a mass, the Earth also has a mass, and the force that exists between massive bodies is what we call the gravitational force, and it is attractive. It is not repulsive, it is always attractive. Alright, so there is a gravitational force that acts between we massive bodies and the Earth, and the weight of our weight is always directed towards the Earth's surface. So the gravitation, the weight is actually provided by the gravitational force. So let us analyze for planet P. So your weight is always equal to the gravitational force between you and the planet. So and the gravitational force is given by G, the mass of the person, the mass of the planet, divided by the square of the distance separating the person and the planet, and the center of the planet specifically, which is just the radius of the planet. So we clearly see that the mass of the person is going to cancel, and definitely we are going to have that the gravitational field strength of everybody is given by the formula, the gravitational constant, which is capital G, times the mass of the planet divided by the square of the distance separating the center of the planet and the center of the body. So this is a gravitational field strength, which is G. Alright, so we have this value already. We have this value for planet P. Now we need to find that value for planet Q. So let me write down the same thing for planet Q. So this is a value for planet P. I'll just call it GP. Okay, so that's the formula for planet P. Same thing happens for planet Q. So GQ will still give us G, but this time around it's going to be the mass of Q divided by the radius of planet Q squared. Alright, so this is what we need to look for. Now if we come here, we realize that the missing term here is the mass of Q and G, because according to the table we have here, we have the radius of Q. So how then do I find the mass using the density? So I'm going to have here capital G, I'm going to have here the radius of Q squared. Here, what is the mass? The mass is the density, so the density of Q times the volume of Q. That is mass, density times volume. Alright, so in simplification we are going to have G, then what is density? A planet is a spherical body, so density is like the density of a sphere, which is 4/3 pi radius of Q cube, then times so that's for the volume, sorry, okay, that's the volume. So I'm going to have the density, let me put the density there, the density of Q. Here is the volume of Q, then we have to divide everything by the radius of Q squared. Now in simplification we are going to have G, the radius of Q will be in the numerator because it is cube and it divides with square, just have the radius. Now for that pi I'm just going to put it here. For third pile, I'm going to put it here, and I think the last thing we are putting is the density of cure. Alright, and I think probably the same thing happens for G. Okay, so all the simplifications will be the same. We just have to replace anything that concerns cure to P. Alright, now you see that what is lacking here is basically G, because we know the radius of cure, we know the density of cure. Alright, so what is lacking is G. So I'm going to use the first equation to find G. So from this first equation, what is capital G? Our capital G is the gravitational field strength at P divided by everything here. Okay, divided by everything there. That's what we have. So it therefore means that if we want to look for the gravitational field strength at cure, all we need to do is we just take our capital G we have found in the first equation and we replace in the second equation, and we simplify. Once we do that, automatically we are going to be able to find the value of the gravitational field strength. So this is going to give me, this is my G. Okay, that's my G. Then we are going to now multiply it with, this man here. Alright, and then we cancel off terms. For third pile, first of all cancels with for third pile. Now what we are going to be left with will just be the gravitational field strength at P. Then we have the radius of cure, the density of cure divided by the radius of P times the density of P. That's what we have. So let's go ahead and feed the values. So our first value here is 13.4. I'll just feed without units for now. 13.4. The radius of cure times the density of cure. The radius of cure is 8,000 times the density, which is 6,000. So we are going to have so let me just put it there. All the units, the unit of radius and radius will cancel, the unit of density and density will cancel. So the final unit will just be the units of this man. So we are going to have here 8,000 times 6,000 divided by, what about, oh no, it's for P first. It should be 16,000 times 3,000. It should be 16,000, okay, times 3,000, and this one should be now the 8,000 times 6,000. Alright, that's what we have. So the unit is Newton per kilogram. That's our final unit, Newton per kilogram. So all these zeros cancel. We are going to be left with 48, and we have here 48, so it cancels, and definitely we are still going to get back the original value. Alright, so that is our answer. If you love the video, make sure you like the video, comment your difficulties in the comment section. Thank you guys for watching, and see you guys in the next video.